Good morning. First full confession, early morning is not my favorite time of the day. I'm still working on jet lag, and you're probably still working on wherever you were late last night, so we'll try to get through this. So Javier asked me to talk about climate change in the context of sustainability. I assume, let's see, which way is this? I assume most of you are familiar with sustainability as the UN has defined it, Sustainability Development Goals. One of those down here, number 13, is called climate action. It's one of the 17 goals. And so what I'd like to do today is to focus on that topic. It's one that I suspect a number of you have probably studied and learned about, but also imagine some of you may not have gone too deeply into this. So I wanted to start with kind of a basic overview of climate change, what it is, what causes it, and why we care, what the impacts are. Then talk a bit about measures needed to deal with climate change. Key focus on policy drivers and the notion of innovation, which is, I think, at the heart of a lot of the work you're doing, and then talk a little bit about where things are headed. So first, just a primer, a basic review of what climate change is and how it works. Temperature is one of the key measures of climate. We'll talk a little bit about that later. And in the context of the planet, what is it that determines the temperature of the Earth? Fundamentally, it's an energy balance between solar energy coming in and terrestrial energy coming out. So basic physics says that any time an object has a temperature above absolute zero, it begins to radiate. So dynamically, as the sun starts to heat the Earth starts to warm, and it radiates back to space. Okay? And when the incoming and outgoing are in equilibrium, which is what nature will always seek, that determines the temperature. So it's actually a very simple calculation to figure out what the temperature of the Earth would be if it were just a rock, no atmosphere, nothing else around it. We can measure how much energy is coming in from the sun per square meter of surface, and we can calculate a temperature, and that turns out to be about minus 19 degrees Celsius. About 2 degrees below zero Fahrenheit would be the temperature of the Earth if there were no atmosphere. So we wouldn't be here having this conversation. The real Earth has a very thin layer of atmosphere. This is not to scale. To scale, the atmosphere would be thinner than this little black line. It's really kind of like a little skin around the planet. It's really very, very thin. But in the atmosphere, besides nitrogen and oxygen, which is what air is mostly composed of, are a bunch of what are called trace gases, small amounts of a number of other gases and water vapor, which play a rather critical role in this overall energy balance. The characteristic of these gases is that they tend to absorb the energy that the Earth would normally radiate to space. It's kind of like putting a blanket around the planet. So what happens when that occurs? That destroys the balance between incoming and outgoing. So there's more coming in than going out, and that basically forces it. The term forcing is a technical term, actually. It forces the Earth to raise its temperature so that the outgoing, again, matches the incoming solar. So how much of an increase does that involve? In this case, with the atmosphere, the equilibrium temperature would come to about 15 degrees Celsius, around 60 degrees Fahrenheit, which is an increase of 34 degrees Celsius, a little over 60 degrees. So the greenhouse, what's called the greenhouse effect, has actually warmed the planet by over 30 degrees Celsius, around 60 degrees Fahrenheit. So small amounts of these gases have had a dramatic effect on the planet. Again, the major greenhouse gases we'll talk about: carbon dioxide, methane, and nitrous oxides. Carbon dioxide arises naturally from anytime there's fires or combustion of carbon-bearing materials, including biomass, wood, and more recently fossil fuels like oil, coal, and natural gas. Methane also arises through various natural sources, and nitrogen oxides, nitrous oxides as well. So these gases are formed and emitted to the atmosphere from both natural processes and also now increasingly from human activities. And it's those human activities that are really the focus of what we'll be talking about. Over the past roughly 150 years, this is the amount of these different gases that has been generated by human activities, mainly burning fuels for energy, burning coal, burning wood, burning natural gas, burning oil, which is putting more of these gases exponentially into the atmosphere. And as a result, the atmosphere has been changing demonstrably over the last 100, 150 years, again in an exponential way. All of these concentrations have been going up. And the key reason is that these greenhouse gases are different from other air pollutants that we talk about. We've always worried about air pollution, health effects from things like fine particles and sulfur dioxide. Those traditional air pollutants, though, tend not to stay in the atmosphere very long. They react chemically, they dissolve in rainwater. If we stopped emitting those, they would basically come out of the atmosphere in days, weeks, or months. The key characteristic of greenhouse gases is that they don't react, they don't come out of the atmosphere very easily. In fact, they stay in the atmosphere and accumulate over decades, centuries, and even millennia. So even in this room, there are probably some CO2 molecules that were formed perhaps even 1,000 years ago. That's the key characteristic. So you can't just turn it off and expect it to go away. It's kind of like a bathtub with a small drain and a big faucet. We're filling the atmosphere faster than we're draining it, and that's causing the concentrations of these gases to increase in the atmosphere. There's one other gas I didn't mention that's also a very powerful greenhouse gas, and that's water, water vapor, H2O. We're putting a lot of that in the atmosphere as well. The key characteristic is that one doesn't accumulate. When the air gets saturated, it rains, it snows, it precipitates. So water vapor is a very powerful greenhouse gas, but it doesn't accumulate. And so it's typically not even often mentioned. So what's been happening in modern times? Have some of you seen this kind of graph before? This is the concentration of carbon dioxide measured in the atmosphere in Hawaii, in a remote area in the Pacific. A guy named Keeling from Scripps in California set this up back in the late 1950s, and this has been kind of the gold standard of what atmospheric concentrations have been doing. There's this kind of characteristic sawtooth. What's that about? What causes that? You know, why does it go up and down like that? Any idea? It's basically vegetation. So what happens in the summer now? Trees are growing, right? Leaves are growing. They're sucking CO2 out of the atmosphere and magically converting it into growth. So when that happens, the concentrations in the atmosphere measurably drop during the summer months. What happens in winter in the northern hemisphere, the leaves fall, they decay, they put the CO2 back into the atmosphere on an annual cycle. So you can actually measure that noticeably. It's a couple of parts per million. The key is that relative to where we've been for the past several thousand years, which is a level of a little less than 300 parts per million, 280 parts per million, we are now actually above 400 parts per million. So what does that mean? What kind of context? We're on a pathway where that 400 could potentially double by the end of the century. It kind of depends on how much more CO2 we put into the atmosphere. But to give it context, this is the picture that always keeps me up at night sometimes. This is about roughly almost 1 million years of history. So these are reconstructions of past levels of CO2 from ice cores. You go up to the Antarctica, you dig down, you're basically going back into history. You measure the CO2 in trapped air bubbles. So that's 800,000 years ago, a little less than 1 million years ago. Here we are today. So you see there's this kind of characteristic cycle that, of a couple of 100,000 years that has to do with long cycles of how the Earth rotates around the sun. But look, over the last 1 million years, here's 400 parts per million. Here's where we are today. Over the past 1 million years, we've never been that high. It's always been down around 300 million years. Where are we headed? That depends on how much more CO2 goes into the atmosphere over your lifetimes and your professional lifetimes. But right now, the pathway that we're headed on, let's see, is this working? Oh, here we go. Okay. That's the pathway we're on. If CO2 were to double by the end of the century, which is not inconceivable, we would be in a situation where nothing like this has happened in literally millions of years, both for the magnitude of the level and also the rate of change, how quickly things would happen. So what? I would always ask you to ask the so what question. Okay? So what? The so what is that as CO2 is changing, the blanket of the Earth is getting thicker, and so the Earth has to respond by increasing its temperature because it's trying to seek a new equilibrium. Here's some data as to what has actually happened and measured over the last roughly 150 years. There's no doubt that the Earth today is roughly 1 degree Celsius warmer than it was about 100 years ago, roughly 2 degrees Fahrenheit warmer, the average temperature. This is history. Some of these temperatures, which way do we have to point here? Over there. Whoops. So you go back. As a lot of you know, recent years have been some of the hottest on record. I'll show you some other numbers. The other important thing to kind of keep in mind is that, as in lots of other things, when you talk about averages, that kind of disguises a lot of important details. One of those is that some parts of the planet warm faster than others. Typically, the polar regions, you see, warm faster. These are pictures. These, again, are actual historical records of the difference in temperature in different regions relative to the average. So basically, the blue areas mean, in general, regions that are colder than the average, and the red areas are regions that are warmer than the average. So look, over 150 years ago, the northern regions, even parts of Europe, dark blue, were generally colder, as you'd expect. But gradually, here's 50 years ago, they were still colder, but not nearly as much. And today, those regions are actually warmer. The Arctic today is about 3 or 4 degrees warmer than the average temperature. So averages don't tell the whole story at all. These distributions matter a lot. This is where the ice is. That's ice that's starting to melt more rapidly than than one would have guessed. So what does this mean looking forward? Here are these are now projections of how things would change if the concentration of CO2 were to double over its current level. And you see the implication is a lot of warming in the northern latitudes, in particular relative to averages, and in terms of overall averages by the end of the century, we're talking about ranges of potentially 3 to 4 to 5 degrees Celsius average, roughly twice that Fahrenheit. And so again, so what? When you look at the impacts, the question is there anything here to worry about? And the answer is yes. This is an eye chart. You can get a copy of the slides later. This is a summary that was put together by, have you heard of the Ipcc? Ipcc is the Intergovernmental Panel on Climate Change. It's basically a group of hundreds of scientists and government folks who come together typically it's been a rough cycle of every 4 years to study the kind of state of the art of climate science and technology and impacts. And they put this information together in one of the recent assessments. On the x-axis is the average global temperature from 0 to 5 degrees Celsius. And these are the different kinds of impacts that have been studied and are known to happen. Water availability, effects on ecosystems, the ability to grow food and crops, effects on coasts, particularly sea level rise as oceans rise in response to both warming and the melting of polar ice, and effects on human health. And you can't see it, but there's a gradation in the colors that get darker toward the right side of this picture. And a lot of the details talk about what some of those impacts are. We'll look at a couple of them in the middle. The consensus today, and it's been this way for a while, is that if the global average temperature rises more than roughly 2 degrees Celsius over pre-industrial levels, over the levels about 150 years ago, we're in a region that is would generally be considered dangerous. There are both potential impacts and potential irreversibilities, things that you just can't go back once you've crossed what's called a tipping point. So we'll keep in mind this 2 degrees Celsius. That's now become kind of the international goal in climate mitigation, trying not to exceed a 2 degrees Celsius rise in temperature. Recognize that we're already at about 1 degree. The other thing I wanted to kind of impress on you, again, this is one of the things that doesn't come through easily when you look just at averages. An average is always a number that is part of a distribution. So if this is temperature, for example, and this is the average temperature, these are cold temperatures and these are warmer temperatures. And we know that we always have some cold days and some particularly warm days. And because this distribution squeezes, there are relatively few what we would call extremely cold days and typically relatively fewer extremely hot days. So what happens when the average temperature increases by not too much, 1 or 2 degrees? That's going to just take this whole distribution and just shift it a little bit to the right. When you do that, though, the tails of the distribution get affected much more dramatically than the mean. So when you started over here, if you could see that outline, and you move it over a couple of degrees, at this end of the spectrum, what used to be extreme cold days, you don't see as many of those anymore. You're just more in here. At this end of the spectrum, what used to be just a few extremely hot days now occupies a much larger region. Hot days become more frequent, extreme cold days become less frequent. So this notion of extreme events and the frequency of extreme events is really the purpose of this picture. And one of the things, when you ask, so what, those are some of the things that we care a lot about. We've seen some evidence of that just recently. So what is climate? I should have saved this for a question. What's the difference between climate and weather, for example? Do you know? So technically, climate is defined as average weather, average actually over a 30-year period. And what are some of the measures, measures of weather? Temperature is clearly one of them, and there are others. Precipitation, that has to be Vodafone. They're my favorite customer, okay? I put together some data for, since we're in Valencia, let's talk about the climate of Valencia. I don't know if you've studied it. I hadn't either till I dug up some of this information. So here's some data for the most recent 30-year period in Valencia. The average temperature, 18.5 degrees Celsius, is around 65 Fahrenheit, very comfortable average temperature. Like many other places, it's colder in winter, hotter in summer, so we're right now in July, where peak temperatures typically are a little shy of 30 degrees. Typically in the 80s would be the high, average temperatures in the mid 70s. Here's another measure of climate, the annual average rainfall, which determines water supply, the ability to grow crops. We're in a very intense agricultural region, as you may know. July is typically the driest month of the year in this region. Most of the rainfall occurs in the fall, and this is the average trend. So when these measures start changing, and the extreme events start changing, it has impacts of the sort we'll talk about in a second. Another measure of climate, these are average numbers, are the extremes that we talked about earlier. I dug up some data on extremes for Valencia. They measure temperature out at the airport and also down at the city center. The coldest day on record in Valencia, the coldest day, minus 7 degrees Celsius. That's about minus 2 degrees Fahrenheit for the rest of us. We would love that to be the, I'm sorry, that's about minus, it's about 19 degrees Fahrenheit. We would love that to be the coldest temperature in Pittsburgh, right? That occurred in 1956, 60 or 70 years ago. Yeah. Say again?
The red line on the rainfall goes opposite the pattern of the blues. I wasn't
Let's see. This might be cumulative. Yeah, what's this red line? I'm not sure, Stephanie. It's a good question. I didn't notice that. Oh, that's right. Of course. Yeah, it's this same. Thank you. It's this same line because here's the temperature scale, and here's the rainfall scale. Thank you. Yeah, I knew I had looked at this before. I haven't woken up yet. Yeah, this is the same as that line. They're both on here. So the lowest temperatures on record are really quite old. What do you suspect the highest temperature around this part of the world has been? 40-something. Yeah, 43, which is about 113 degrees Fahrenheit. What was the highest temperature in Paris last week? You know that? Paris had a record high last week, 114 F, about half a degree more than that, 45.5 degrees Celsius. Paris is substantially north of us, and it has just had an extreme temperature higher than the highest temperature on record here in southern Europe. Okay? And look when this happened, just a few years ago, and a few years before that. So what are we seeing here? We're seeing something that is consistent with the story I just showed you in that distribution, right? We're seeing fewer extreme cold days. These are 60, 70 years old. And we're seeing more recently, more extreme warm days. It's consistent with that shift. We shifted the average temperature even 1 or 2 degrees, and we're starting to see this in the record. And so again, so what? The so what is that these extreme events are happening more often, and they're associated not just with high temperatures where people often get ill and frail people often don't survive, but other types of events of the sort that we see here, ranging from droughts to floods to fires. And we've seen in the last number of years, certainly within the last decade, more and more of these extreme events around the world. So can we say climate change is causing this? We can't say that as a causality. What we can say is that what we're seeing now on the ground today is consistent with what we would expect to happen in a world with climate change. And some of these impacts have already been documented. The Ipcc has been working on trying to document actual impacts today around the world. Again, I can give you the details of this, but these are impacts. The blue is on physical systems like snow and ice and river systems. The green is biological systems. The red are human and managed systems. The point simply is you can look at a global map and see documentation of changes that are already happening. So the message here is that climate change is not one of these things that at some time in the future, we don't have to worry about it today. It's increasingly documented as happening now. Here are some projected changes in Europe, specifically with the effects of water limitations on crops. It's basically southern Europe and Spain in particular that would be hardest hit by these kinds of impacts. So there are things that we're concerned about, and the next question is what could we do about it? And there are generally two general approaches. One is live with it and adapt to it, and the other is try to do something to mitigate future changes. And we're already doing both, and we probably will be doing a lot more of both. And I think this is relevant, I think, to the projects that you'll be doing, because both adaptation and what we'll call mitigation in a minute are really kind of front burner needs. So adaptation means adjusting to changes. Here are some examples of high-tech and low-tech adaptation to changes in rising waters. In the Netherlands, which is below ground, they've been dealing with water issues in dikes for centuries. They've now been installing these kind of high-tech gates that can open and close and basically put up a physical barrier to rising river waters during peak times. Here are some folks in a South Pacific island trying to plant some trees against encroachment of water on an island that may no longer exist in the next 100 years because of rising sea levels. Okay? Here's another example of adaptation. This one's in Alaska. This was a coastal village that is now being moved. The village basically decided we can't stay here anymore. We're getting battered by increasing number of storms. Our land is eroding. So the village voted to actually move a couple of 100 miles inland. Another type of adaptation. Again, these things have also been studied a bit, and there's some literature on the ability of different regions of the world, given what we know today, to adapt to the kinds of changes that are expected. Here in Europe, I would circle some of the impacts that are associated with southern Europe, where we are now in Spain. The most pressing impacts are higher temperatures, extreme temperatures, and what they call drying, basically desertification. There's a lot of concern in this region and documentation of less and less rainfall and the ability potentially to start approaching desert areas. There have been some studies of the ability of different regions to adapt to these kinds of changes. The bottom line, as you might have guessed, is that social and economic systems and the kinds of planning that a lot of you are involved in will play key roles in determining both the future risks of climate impacts and resiliency to climate impacts. This is going on everywhere. In the U.S., probably one of the poster child that I'd call your attention to in the U.S. is Miami, Miami Beach. Miami is already starting to feel the impacts of sea level rise. Many of the downtown streets are flooded year-round. Miami is spending a lot of money now to put in pumps to try to pump water out of city streets. And in some parts of Miami Beach, they're spending a lot of money to literally raise the street a foot, digging it up, planting new concrete, and raising the sidewalks. This is going on today. Things like that are going on in Tokyo and other parts of the world as well. So stuff is happening, and it has costs. So the other type of measure is called mitigation. This is basically trying to reduce greenhouse gas emissions. Adaptation, you're always chasing a moving target if things are continuing to increase. And so here there again are a fairly well understood set of measures that are both needed and are feasible. New and improved methods to reduce CO2 emissions. CO2 is the major greenhouse gas. There are several others that I didn't mention as well, but CO2 is kind of the elephant in the room. It's about 80–85% of the problem. It's not the entire problem, but it's the major one because we burn so much stuff. About 85% of our energy comes from burning fossil fuels globally. It's a huge investment. So anything we can do to reduce CO2 emissions from energy use in buildings, that'll be particularly of interest, I think, to some of your projects. Energy use in industrial processes, less so. Energy use in transportation systems, to the extent you're involved in planning areas where transportation is kind of an integral part of a design, that's also kind of important. Reducing other greenhouse gas emissions from agricultural activities, industrial processes, and so on. Again, I don't know how much you all know about Valencia. One of the major crops here is rice. You know that? Were you aware of that? Javier knows it. Have you been to the Albufera? You haven't? Just a little south of here is a huge lake, freshwater lake called Albufera. It's just literally adjacent to the sea. Huge rice growing area, which they turn into wonderful stuff called paella. You've had paella, right? But rice is also a crop that, by its very nature, it grows below water and it generates methane. Rice is a major food product in the Orient, around the world. It's also a major source of methane. Methane turns out to be pound for pound or molecule for molecule about 25 times more potent than CO2 in its ability to trap gases. Doesn't last quite as long in the atmosphere, but it's a very potent greenhouse gas and another kind of concern. And finally, enhancing natural sinks for carbon by growing trees, soil management. That little cycle that I showed you earlier in that CO2 cycle is really critical. The amount of CO2 that is taken up by vegetation today is roughly 25 or 30% of the total budget. So in parts of the world that are being deforested, that's basically putting more carbon back into the atmosphere in a serious way. So these are all, again, things that, that are involved in mitigation. But the question is how much? How much is needed and how can it happen? And again, the key message here comes from what the goals are. Right? So if you want to deal with climate change, what are your goals? How do you know when you've won? The goals that were set out for climate change were set back in 1992 at a major United Nations conference held in Rio de Janeiro, which resulted in a document called the Framework Convention on Climate Change. It's a convention that virtually all countries of the world have agreed to, which tells you that the only way everybody agrees to something is when it doesn't really require you to do anything, which is what this does. So this is a framework convention where everybody agreed that this would be the goal of climate change. The goal is to stabilize greenhouse gas concentrations in the atmosphere, those concentrations that are rising exponentially now. Try to stabilize that, level them off. At what level? At a level that would prevent dangerous anthropogenic interference with the climate system. Okay? Basically a level that would prevent dangerous effects. So these words, when I first saw them, it was clear that these words were not written by engineers because they're just very fuzzy, right? There's no specific goals. Doesn't say by when. This had to be written by lawyers, not engineers. And yet, when you look at the implications of this, as fuzzy as it is, lacking details of timetable, and the technical implications are actually rather profound, because you can go back and ask, well, what does it take to stabilize that concentration, independent of what the level is? What would it take to stabilize it where it is today, or 50% more, or 100% more, in different time frames? What would it take? And that's something you can get a handle on. Again, the best analogy I know of is the bathtub analogy that I mentioned earlier. If you think of the atmosphere, if you think of it as a bathtub, we're filling the bathtub with gases that are being emitted, but there's a very small drain because these gases don't react and leave the atmosphere very quickly. So if you want to stabilize the level in a bathtub, what do you have to do? You've got to turn the faucet down to match the drain. Right? Otherwise, it's going to keep rising. So how much do you have to turn the faucet? And the answer, unfortunately, is not a little bit, but a lot. Again, it depends on how quickly you're filling it up. But based on kind of where we are now and some scenarios about where we might be in the next several decades, we've got to reduce emissions by 50 to 85 or 90%. The better estimates now are toward the higher end of this range within the next several decades. It's really the concept of a carbon budget. There's only so much carbon the atmosphere can hold before the warming will start to increase. So if we were dealing with a problem where the solution was we we need to reduce emissions by 5 or 10%, and we can call it success, we'd be in a different world. But we're in actually in a world where we need big reductions in a fairly short period of time to reach these kinds of goals. That 2-degree goal that I mentioned earlier is a goal that is still operable. A goal of not more than 1.5 degrees was put up as a challenge. I'll get to that a little bit later. As well by the UN framework, and that would require these kinds of reductions in even a shorter time period, 2040-ish or so. There was a big report out last year on that. So that's the nature of the challenge, big reductions in a short period of time. And the question is, are there opportunities for doing this? So on a more positive note, I want to just point out many of the opportunities. I'm starting, this is a picture of the U.S. energy system. On the left are different sources of energy. So there's solar, nuclear, hydro, wind, different sources of energy. What we use energy for are these things on the right. We use energy for transportation, for industrial processes, and in commercial and residential buildings. That's the energy demand side. This is the demand side, that's the supply side. There are different routes for getting there. Different fuels are favored for different types of activities. And in the middle is that important box called electricity generation. Electricity is something we've come to rely on for a lot of energy, and that electricity is used primarily in buildings and in industrial processes. But it's these last two boxes that are especially interesting in terms of potential. This darker one is called energy services. This is the amount of energy that we actually get some value off, the energy that gives us mobility and comfort and all those other things. This is the energy we waste, that we throw away, that we don't get any value off. Around 2/3 of the energy that we start with is in that waste column. About 1/3 is useful. Right? So we're throwing away literally 2/3 of the energy that we that we mine, which is the source of emissions. Why do we do that? Are we really that dumb? Are we really that incapable? Well, if you look at where that comes from, there are some things, some technologies that we have that are fundamentally not able to use all that energy. It's thermodynamics, it's physics. Most of that actually comes from generating electricity. You see these gray bars. Electricity and transportation are the two biggest contributors to that. So internal combustion engines that have efficiencies of about 20%. 20% of the gasoline we burn actually goes to moving the car. The rest basically goes out. Hot engines and hot tailpipes. Same with power plants. We can think about other technologies, both for using some of that waste heat and other ways of providing these services that don't have as much waste. So this is always a nice place to start. And then when you dig down into some of the details, here are some things on the demand side that we can do. The first and usually most cost-effective set of measures is to try to simply use less energy to get the goods and services you want, energy efficiency. So using energy more efficiently in buildings, in industrial systems, and transportation systems, to the extent efficiency can reduce the need for primary resources and emissions, that's good. And if you look across the spectrum of technologies, there are in all of those areas, buildings, transportation, and industrial processes, there are always examples of what I've called best practice. There are some people that do things better than others, more efficiently than others. There's a lot of literature on this, and so the question is, why the hell aren't we using that? And often the answer is anything from, well, I didn't know about that, or it cost a little more, or the other guy's just smarter than I am and I haven't figured it out yet. There are a variety of reasons we're not using that, but just in terms of a few examples of what exists that we are not using to a fullest extent, they include a variety of appliances, some of which are more efficient than others. Lighting is starting to transform. We have LED lighting and other types of systems that are moving away from traditional incandescent bulbs. Here's something, again, I don't know how well this is known in the architectural world, but cool colors. There are different types of paints and surfaces that have higher reflective properties and basically require less energy for heating and cooling. In the transportation area, we're starting to move away from traditional internal combustion engines to things like hybrid electric cars and fully electric cars. Hydrogen fuel cells is a technology that also has been kind of coming and going. Right now it's more on the going side, but it's another type of technology that can get away from traditional gasoline fuels. So that's kind of at the level of individual technologies. The other key area, though, on demand side and more difficult things are things like community planning and development, things which collectively reduce demands for energy and energy-intensive services, changes in things like community planning, transportation planning, agricultural processes, and a lot of personal lifestyle issues. The kinds of foods we eat, for example, have a major impact on the resource requirements. So many of these things transcend away from purely technical and technological into behavioral changes and social changes that are typically more difficult and longer lasting. But we have a lot of examples of things like this that have happened. Again, here are some examples. Here in Valencia, this city is kind of ideal for bicycles. It's fairly flat. If you look around, you'll see a lot of those bike stations. You'll see a lot of streets still torn up, being remodeled with fewer lanes for traffic and more lanes for bicycles around the city. A lot of that is well underway. Some fairly efficient transportation, and lots of regions, particularly in the city center here, where what used to be streets are now just for pedestrian and services. This is one in center of town. So these are things that are happening in different parts of the world, and examples of those other kinds of things. Yeah, I included this slide just to kind of remind myself to tell you. It's often said, if you listen to, in the U.S. particularly, a lot of Republican candidates for president, they'll say, we can't deal with climate change because it's going to ruin the economy. Ruin the economy is always the first kind of reaction after you accept that maybe we actually have to do something. And here are some examples that show with actual data that isn't necessarily the case. This is what happened in the U.S. In the last half of the 20th century, when the first energy crisis raised the world prices of oil substantially. Oil got 10 times more expensive, and as a result, the system reacted. It got more efficient. We restructured the economy, and basically, this black line is energy per unit of GDP, per unit of wealth. Energy use decreased substantially relative to what it had been. At the same time, this is GDP per capita. the average wealth of an individual. Right? So energy came down, people got richer. The notion that people will get poorer and the economy suffers if you reduce energy demand is clearly not the case. We've got evidence that can happen. See, I want to get through quick. On the supply side, this is probably of less interest. Again, supplies of energy moving away from carbon-intensive fuels to renewables is something that is, again, underway. Another option is to, this one you may not have heard about, I mentioned this, is to capture the carbon, the CO2 from large industrial sources and power plants before it can be put into the atmosphere. There are examples. There are two large power plants, one in Canada and one in Texas, that are doing that. The CO2 gets compressed into a liquid and gets pumped deep into a geological reservoir where it stays out away from the atmosphere. We can do that on coal and natural gas. Again, a reminder about the scale. This is an issue that is going to require new technologies on a large scale and require a lot of innovation in lots of areas. Let's see, I'm running a little late, so I'll kind of rush through this. Just a word about the process of innovation, which is something a lot of you will be involved in. Innovation was generally viewed as, there are different processes called invention, innovation, adaptation, diffusion. The traditional notion was that you get an idea and it's kind of a linear process, right? So if you wanted to innovate, all you need to do is throw money into research and development, and the better mousetrap is going to appear automatically. This has been a very prevalent view around the world for many years. It's one that basically says we just need to keep pumping money into R&D. It's very attractive, and its only flaw is that it's wrong. It's not really the way the innovation process works. The innovation process is actually a much more dynamic process with a lot of feedbacks among all these different steps. It involves not only R&D, but things called learning by doing and learning by using. And so if you ask, what do we have to do to encourage innovation to get a lot of the new technologies and new social systems? The answer is you've got to support all of these areas, not just research and development. Government actions play a critical role in this. There are lots of things we can do as individuals, but without government actions, it ain't going to happen. Effective government policies are critical. And there are basically two types of government policies, incentives and requirements. I call them carrots and sticks. It turns out, what do you think people prefer? In general, people prefer carrots. And in the climate area, most of what we've been doing over the last decade or two has been supplying carrots, various types of incentives, and not so much on sticks. Those incentives are support for R&D and things like tax credits and other kinds of voluntary measures that individuals and organizations can take. These are examples of sticks, things like taxes and regulations and standards. There are some examples of those as well. Let me give you just a couple. In terms of carrots, one of the big successes is actually various types of subsidies and incentives for renewable energy, wind in particular and solar as well. As a result of a lot of those incentives, wind has been the fastest growing source of new electricity, not just in the US, but here in Europe. An example of a stick is something called a renewable portfolio standard. Many states in the US have adopted requirements that a certain fraction of the state's electricity must come from renewable sources. That's not an option, it's a requirement. Together, those two types of measures have dramatically brought down the cost of renewable energy. Wind and solar energy are now a fraction of what they were or believed to have been as a result of that. So government actions, both carrots and sticks, can be critical in developing new technologies and bringing them online. In the building sector, this has also happened. The poster child for this has been energy use by refrigerators. Refrigerators back in the 1970s was the most energy-intensive appliance in a typical household. And then California, which has always been a leader in environmental issues, said, if we keep going, this is the energy use by refrigerators and numbers, we're going to have to build a lot more power plants to supply all that electricity just to run refrigerators. And so California said, enough, we're going to have to introduce efficiency standards. If you want to sell a new refrigerator in California after the mid-1970s, we're going to look around and set standards that are already being met by the best manufacturers today. So they did that, and guess what happened? Energy use started turning around. Shortly after California adopted some standards, the U.S. government adopted standards as well, and energy use has declined. The typical manufacturers respond, oh, it's going to put us out of business, and nobody's going to be able to afford a new refrigerator. This is the price of refrigerators. True enough, initially the price did go up because you had to have more insulation and so on. But then innovation kicked in. People figured out how to do things in a more economical way, and prices started coming down. So today, refrigerators on a normalized basis use much less energy and cost less, and to boot, they're even bigger. The sizes have been getting bigger. The size of a refrigerator today is pretty much limited by the size of the door you have to get it through. So this is kind of a triple success story. For California, it avoided construction of a lot of new power plants. Had it not been for the standards, this is how much energy would have been needed. Only a third of that was actually needed, and these were power plants that were not built and didn't have to be built. So that's the kind of thing we need more of. There's a similar story in the automotive sector with fuel economy standards that have transformed that industry. And between electricity use and automobile and transportation use, those are the two biggest areas where improvements in greenhouse gas reductions can be made. I've just got one or two slides left. I think many of you already are aware that in terms of international efforts to address this problem, there was an agreement a couple of years ago in Paris on a new agreement where basically all countries of the world agreed to set binding commitments for reductions in greenhouse gas emissions. Each country would decide for itself how much reductions. The goal again was to keep temperatures well below this 2-degree level and to endeavor to limit the rise to no more than 1.5 degrees. So this is the current international policy context. This is still a work in progress. Some countries are meeting goals and others not. The goals that were set initially are just a fraction of what ultimately is needed. There was a lot of optimism at the time this was done. There's probably realistically less optimism in the world now because the U.S. is planning to pull out of this agreement next year. We'll see if perhaps another president might reverse that, but that's the glide path we're on now. The U.S. has generally been a leader in this, and so when the U.S. pulls out, other countries slow down as well. So this is still a work in progress. Again, here in Valencia, there's a mayor here who does take this problem quite seriously. So if you look around, there are plans. The kind of work you're doing in these projects will be, I think, well appreciated and well received, and will make a big difference. In general, the kinds of activities that are needed are probably a combination of carrots and sticks, a combination of regulations and innovations. Right now, we're most lacking, my judgment, on on sticks. We've got a lot of carrots out there, but the sticks turn out to work a lot faster and really are what needed to get down. And one particular challenge that I wanted to leave you all with, you're going to be doing some projects involving buildings, and as I was mentioning to Stephanie earlier, I think one area that I think there's a huge lack of leadership in and models for are performance standards for buildings. Some states have done this, but we don't have any good models at national levels or others. How can we, in the same way we require new cars to be certain to be efficient, we require new power plants and other new technologies to meet standards. What kinds of standards would be appropriate for buildings and urban developments, the kinds of projects you're working on? What should we require builders to do in order to move in that direction? Something to think about in these projects. So here's my crystal ball that we use in graduate student meetings, trying to see what the future will bring. Again, the Paris Agreement is just the first step. Most urgent need, I would say, is for strong policy drivers that spur innovation. Basically, you've got to create markets for new technologies. A lot of these things have no markets unless you have a regulatory forcing function. Along with that, leadership at all levels, both public and private. And my hope and expectation is that many of you will be providing that leadership. So the future is in your hands. We'll see what future policy drivers emerge. And with that, let me stop and take a rest, and thank you. Good. Okay. I think we got a late start, but yeah, is there time for a question? Yeah.
Do you think that there's a specific role for countries like the U.S. and China and India to take when it comes to, when we saw the SDGs, number 7 is to have 100% electrification, and a lot of that is in sub-Saharan Africa, but the population growth is also going to be pretty insane in the next 20
Yeah.
50 years. So what do you think the role of countries like the U.S. and China and India is to help with mitigating climate change effects that may be less possible for low-income countries?
I think there are two kind of roles. One, which are commitments that we made, are basically to provide some direct financial assistance, particularly to developing countries. Don't do it. You can't do things for them. Just give them financial help and guidance. China is, I consider China now a developed country. It's the myth that China is still an emerging country, I think, is really no longer the case. And they're already doing a lot of that thing. So that's the easy thing. The one that's more intangible, but I think has historically been most critical and will be going forward, is leadership by example. In all of the environmental issues that I'm aware of, U.S. leadership has been critical. I got involved in this back many years ago in looking about air pollution, just as an example. The same is true in various water areas and other things. When the U.S. committed to solving air pollution problems and developed new technologies, I'm thinking of power plants and cars and factories, it starts getting imitated. The first imitations actually were here in Europe. They started adopting, for example, automotive efficiency standards that were developed in the U.S., in Canada. In some cases, leadership came from places like Japan, and that was one case where they were out ahead of the U.S. in certain areas, and we later adopted their technology. And that, I think, has had a critical impact on China, which did not want to be perceived as a technological runner-up. They wanted to play with the big boys. Okay? So when that happens, it's the same thing that happens among groups of people. You know, you see your buddies running a little faster, than so you run a little faster too. That's what leadership does, and it's kind of been documented. So I am still optimistic that the U.S. will provide that kind of leadership. It already is in many ways. It's not happening at the national level today with this president, but it's happening at state levels. We look at what California, again, has been doing and a number of other states. We look at what a lot of corporations are doing. So leadership by example is really critical. People copy that, they get ideas, and that accelerates things. Okay? So I think it's a key role. The next round of leadership is going to be, I think, in putting in place a lot of the requirements that only governments can do, that says, look, if you want to do business, you can't do it by emitting a lot of carbon, and here are the limits that need to be. That creates markets and incentives, and that's the other kind of leadership that is, I think, most sorely lacking. Stephanie, you were going to...
I want to expand on that because that works at different levels. You're saying how critical it is for the whole building industry to
Right.
move its energy use. That's worked by example better than any other way.
Yeah.
The government, just like your example of the refrigerators, government regulation has followed the demonstration that we can achieve these. So a simple model, something like the development of the marina, can have a huge impact because it then serves as context and standard for future development. And I think even what the you're using, like looking at best practices, is a demonstration of how important those are in the dynamic of overall change.
Yeah.
And so that private and public kind of ping pong back and forth can move us quite
Yeah.
quickly.
And it's a bit of a chicken and egg game too. I think a lot of these things start by somebody decides to do something. You decide to do a project, and then you suddenly realize it has this benefits. Then somebody else copies it, and then at a certain point, government can step in, right, and say, hey, why don't we require everybody to do this, right? Because if we do, it will have benefits that we all want socially, and the only way to get those benefits, look, nobody's going to spend $1,000 to put a catalytic converter on your car if you're the only one, right? It's only a government, our collective actions, that say the only way we're going to get the collective benefit of reducing emissions, in this case, is if everybody does it. But people have to go along, at least in a democratic society, okay? And so you look to the examples. You look to people who are actually doing it to show that, yes, it can be done. And then at some point it becomes politically acceptable, and you have this sea change. We need more of those kinds of things, especially in buildings.
Yes, absolutely. And that's great because it's at a scale where we can create models with, it takes just a few really
Yeah.
enlightened progressive clients to do that. I think another factor is the private insurance industry that is moving us, whether we like it or not, toward action that government can't do.
Yes.
But when it becomes too expensive to rebuild your house in Miami, when the real estate values don't get appraised at the value they need to, it will move us out of those dangerous places.
Absolutely. Absolutely. Yep. Yeah.
That's a good point.
Yeah. There's really two scales, right? I mean, there's a scale at kind of an individual facility or a technology, but the critical one is the social system, right? The way we choose to live. Are we building more urban sprawl, or are we building out, or are we building up? Right? Those are the kinds of things that also make huge huge differences where where guidance and standards are really critical. We're not of a single mind on that, but those are the kinds of areas we need to move in. Anything else? Yeah.
Yeah, on the idea of leaning more states. So one of the main policies that's been introduced right now, at least in North America, is the carbon tax.
Carbon tax.
And at least in Canada, and I believe the States, or even the CAPE standards, they're requirements that have been set up by the government.
Right.
But at the same time, they've had a lot of recoil.
A lot of.
Recoil. So a lot of people
Yeah.
come out against it. So how would you develop policies that people won't necessarily come?
Yeah, the devil's always in the details, right? In those kinds of things. So I'm personally of two minds with regard to carbon tax. There's a lot of talk about it because there are a lot of economists working in this area. Economists are very articulate people. They're always confident. And yet you see when governments try to impose taxes, like France is another example. They tried to raise gasoline taxes a few months ago, and there were riots all over Paris and other cities. In other cases, in parts of Canada, it's worked. Part of it is the way you structure these things. So if you talk about a tax, the question is what happens to the money that you collect in the tax. In Canada, they're returning it directly to the people, sending people checks. Okay? People like to get checks in the mail. In other cases, the notion is we're going to use the money to invest in new technology, so it kind of goes into a government coffer. People don't see any direct impact, and those, I think, become more difficult situations. I've got a personal preference for regulations and standards, in part because it doesn't make the prices explicit, and it tends to result in often more immediate changes. Again, it depends on how you do things, but when you tell an industry that in order to do business, you must meet these standards or regulations, there may be a lot of crying and bitching and moaning about that earlier, but if you pick things that are reasonable and doable and yet challenging, there's just a lot of evidence that says it gets done. Everything I showed you here, from standards of power plants, automobiles, to refrigerators, it gets done. It's the certainty that says, in order to stay in business, this is what I have to do. And once that gets set, then a lot of smart people get to work and things happen. Okay? If you ask, well, what did it cost per ton of CO2? It's probably the level of a carbon tax that would be politically unacceptable. Because that's what it's going to take to get a lot of these big reductions. You don't get big reductions that inexpensively. Okay? So I think, at least in democratic societies where the kinds of carbon taxes and prices that have been talked about are on the order of a couple of tens of dollars per ton of CO2, for example. Okay? What it takes to get 50, 60, 80% reductions are probably in the order of hundreds of dollars a ton. But we've got examples where that's been done. That's been the implicit price, but it's been done and it's been acceptable. So it's that combination. It depends on the political and social context of where you are, but there are a number of approaches for doing that. And historically, at least, regulations and standards have had a bigger impact on bringing these reductions down. If you look at what the state of California is doing, so California has a greenhouse gas policy. They have very ambitious standards for the next several decades, and a variety of policy mechanisms for achieving them. So California has not an emissions tax, but a cap and trade system. which is another way of doing it. It basically goes directly to the goal of the cap. This is how much carbon we're going to allow into the atmosphere. If you want to emit a ton, you need a permit. We're going to issue some permits initially, and then the market will buy and sell. Some people can do things inexpensively, and they can sell their permits, and other people may need to buy them, cap and trade. They've also got other regulations. They've got fuel economy standards. They now have building standards. They're going to be starting to require solar energy in new houses in California. So it's a combination of kind of economic forcing functions in the cap and trade system and regulations and standards. The brunt of what is going to be, what has already happened and what is projected to happen is going to come from the regulations and standards side of it. The combination of the two, though, is, to my mind, ideal because if you've got something like a cap and trade system, it kind of creates an extra incentive to overachieve on the performance side. The classic criticism of regulations is that it kind of freezes things into place. It doesn't allow for innovation and development. You set a standard today, and even though you could do better 5 years from now, you still have the old standard, and so it's not as efficient in economic terms. But if you have a market system in parallel to that, then you do have a bit of incentive. If I'm required to do 80% reduction, and for a little bit more I can do 90 or 95% reduction, I can basically sell those extra credits in the market and make a little extra money. It's an incentive for me to do that. So that combination, I think, is the most productive way of doing that. You'll still need other kinds of incentives to get certain things going. Again, we've put collectively in the world something like, I think numbers on the order of $20 or so billion in subsidies for renewables. It's had a huge payoff in terms of reducing the price of those. So subsidies and various other types of government actions on the carrots side of the ledger are also going to be needed. It's a combination of those. I think that is likely to be the most productive path forward. But first, there's always going to be political resistance to overcome. Okay, have I worn you out?
It's not directly related, but I have a mixed feeling.
Yeah.
What about electric cars?
Electric cars.
Because my personal opinion is that they are not good for climate change.
Well,
They are needed in big cities due to CO2 concentration, NOx, and a number of things. They're needed, but as regards to climate change, they are negative.
it all depends where you get the electricity from. Right? So if you get the electricity from a coal-fired power plant, not so good. If you get the electricity from a solar or a wind plant, not so bad. And that's kind of the direction we're moving in. It looks like electric. There's been a kind of a running. I was going to say it's not a battle. Well, there's basically three options for transportation if you want to get off of petroleum. Right? One is electrify, but it has to be from low or no carbon electricity sources. The other is hydrogen, fuel cells. So we have hydrogen fuel cell powered vehicles in California today. As an example, but the question is, and hydrogen, you burn it, hydrogen and O2, H2O, but the question is, where do you get the hydrogen from? Because hydrogen is not something that occurs naturally. You can't dig so you have to get hydrogen from some other source. Today we get hydrogen, do you know where we get hydrogen from mostly? From natural gas. Most hydrogen is produced from methane, from natural gas, commercial levels of hydrogen. You can also get hydrogen from water by electrolysis, but then again, where does the electricity come from to run that machine? You can get hydrogen from various other hydrocarbons as well. But again, you have to do it in a way that doesn't emit CO2. That technology that I showed you briefly of carbon capture and storage is potentially one way of using fossil fuel resources to produce large amounts of hydrogen and capture the CO2 and sequester it. That's one option. Getting it from water, again, depends on where the electricity comes from. So electricity, hydrogen, and those have been the two key ones that have been kind of moving back and forth. But all auto manufacturers have been working on both technologies and still are. Electricity looks like it's winning out because it's easier to handle from an infrastructure point of view. If you ran the transportation system on hydrogen, you need a whole hydrogen fueling infrastructure that is not currently in place and would be cumbersome. But that may still happen. There's a pendulum that swings back and forth between those technologies. It's not over yet. There's one other option, which is biofuels, using biomass as a source of liquid fuels. And that is very much in play as well. Those are the only three ways I know of to get transportation off of petroleum. And it looks like at least two of those three right now have been kind of moving ahead more rapidly. So we'll see how it works. Here in Spain, electric vehicles have not been really prevalent yet, except for Prius's hybrid vehicles that are combinations of batteries and petroleum. That is probably going to be the fastest growing segment for a while, and we'll see if we completely electrify or what. China is very heavily, I think, now committed to electric vehicles, but the issue then is batteries and other kind of storage technologies. So we'll see. Transportation's a tough one. Okay. Yeah.
When it comes to the production of solar cells, batteries, or hydrogen fuel, what of them is the most sustainable energy source? Like by producing it,
To manufacture those things? Well, I cut a couple of slides out. I was going to talk about life cycle emissions. I mean, making anything is going to require energy, right? And so it's all going to boil down to if you're using electricity, electricity has to come from an energy source that is carbon, either low in carbon or carbon free. The amount of energy it takes to manufacture different things, that's also, I think, at play in your question. I don't know off the top of my head what the relative amounts of energy are to make solar cells or certain types of batteries. That's kind of knowable, but I think that's probably not going to be the major consideration. It's whichever technology has the larger role is the one that will get invested in, and it will get better over time, whichever it is. Right now, there's a lot of work going on in batteries, energy storage systems in general, not only for transportation, but very much in the case of electric power systems. So the good news is we've got relatively cheap solar and wind technology to generate electricity, and the bad news is it still gets dark at night, and the solar cells don't work. And there are still days and sometimes weeks when the wind doesn't blow and the wind turbines don't turn. And so what do you do there? So energy storage of various types is the key issues. Batteries of various types are one of the main technologies that are being worked on. A lot of work going on in advanced batteries. That said, and that's going to allow at least electric systems to have increasing fractions of renewables in a reliable way. But once you get up to the really high levels, once you get past 70 or 80%, then energy storage and batteries becomes very expensive at that level. It might get you to 50%, 60% maybe, but then it gets more expensive, and that's where you need potentially other options. So that's where natural gas, which is relatively lower in carbon than coal and oil, but still not carbon free. The notion of natural gas with carbon capture and storage, which can basically almost eliminate carbon emissions as a more reliable backup, is something that's in play. Ultimately, the notion of taking CO2 out of the air in order to get to some of these more aggressive targets, that looks like what we'll have to do in a serious way in the last part of the century. These are other kinds of technologies for sequestering or removing carbon that are also being worked on heavily.